Hello everyone. In this video, we are going to discuss about total internal reflection in nature and its technological applications. We have already discussed about total internal reflection in our previous video. I will provide the link in the description box. If you want, you can watch that. In this video, we are specifically discussing about the technological applications of this total internal reflection and the total internal reflection in nature that we can see or observe in nature. We will discuss about Mirage, then the case of Prism, diamond and optical fibers. So first of all, let us discuss about Mirage. Mirage, it is an optical phenomenon. It is an optical illusion, something that you believe you see but it is not really there. Mirage, it creates an illusion of water on sunny days when driving down a roadway. You might have observed a small pool of water on the road several meters in front of the car. But when you reach at that location, you will recognize that the small pool of water is not there. The appearance of water is simply an illusion. On hot summer days or on hot sunny days, the air near the ground. So you just imagine this as the ground. Okay, this as the ground. A man is standing here, a person is standing here. And actually, the air can be considered as different. We can consider actually different layers of air here. So all these are actually showing the different layers of air. So on hot summer days, the air or the layer of air near the ground becomes hotter than the air at higher levels. Okay, hotter air is less dense. Hotter air is smaller. Hotter air has smaller refractive index. So its refractive index will be less compared to the higher air layers. Okay, so hotter air has smaller refractive index than the cooler air. Alright, that is optical density at different layers of air increases with height because refractive index increases with height. So obviously optical density of each layer of air also increases with the height. Or we can see that if we move from top to bottom, the refractive index decreases. Okay, this region will have more refractive index than this region. And this region will have more refractive index than this region. Okay, so refractive index, as we move from top to bottom, the refractive index decreases. We know that when a ray of light passes from a denser medium to a rarer medium, that is, this layer of air is more optically denser than this layer. This layer of air is more optically denser than this layer of air. Okay, so we know that when a ray of light passes from a denser medium to a rarer medium, what happens? That is, from higher refractive index to a medium with lower refractive index, the light ray bends away from the normal. Right. Now consider a tree here which is on the ground or any other tall object. As light from this tree passes through the medium whose refractive index decreases towards the ground, the ray of light which is actually coming from that or reflected from that tree successively bends away from the normal and undergoes total internal reflection. And if the angle of incidence for the air near the ground exceeds the critical angle. We have actually discussed about critical angle in the previous video. You please watch that video, then only you will get an idea about this total internal reflection. So you see here, we have a ray of light which is coming from this tree. What happens, this region will have more optical density than this region. Okay, optical density decreases as we go from top to bottom. Alright, so this region will have more optical density than this region. So when a ray of light is traveling from a medium with a higher optically denser medium to an optically rarer medium, that ray will move away from the normal. So this ray was actually supposed to go through this dotted line path, but it will not, refraction takes place, it will move away from the normal. Okay. This one is the normal which is drawn at the point of incidence. Again, this ray, when it reaches here, actually this layer of air has less optical density than this layer. So this ray of light is again traveling from an optically denser medium to rarer medium. Okay, so again it moves away from the normal. But when it reaches here, when the angle of incidence increases, or when the angle of incidence for the air near the ground exceeds a critical angle, what happens? This ray will not come to this layer. The ray will be completely reflected back to the same medium. Okay, light seems to, so this is the ray which will be entering to the eyes of this person. Okay, so light seems to travel in a straight line for us. So to a distant observer, the light appears to be coming from somewhere below the ground. That is when we extend, light seems to travel in a straight path. So when we extend this light ray backwards, we get the image of this. Okay, we have taken the rays coming from the leaves. So we will get the image of those leaves here when we extend this light ray. Okay, so light seems to travel in a straight line for us. So for a distant observer, the light appears to be, it appears to be coming from somewhere below the ground. So he would see an inverted image. Okay, that person would see the inverted image of this distant object. So the observer naturally assumes that the light is being reflected from the ground by a pool of water near the tall object. Such inverted images of distant tall objects cause an optical illusion to the observer. This natural phenomenon of formation of inverted images of distant objects by total internal reflection is called mirage. Okay, you might have noticed that while moving in a bus or a car during a hot sunny day, summer day, a distant patch of road, especially on a highway, appears to be wet. But you do not find any evidence of wetness when you reach that particular spot. This is also due to mirage. The water you see on the road is not really water. It is a reflected image of the sky. Now we are discussing about the technological applications of this total internal reflection of light. First we are discussing about the case of diamond. You just imagine this as a diamond, okay? Diamonds are known for their spectacular brilliance. The shining of a well-cut diamond is mainly due to total internal reflection. The critical angle for diamond-air interface, that is, here we have the diamond and here we have air. So the critical angle for diamond-air interface is very small, which is approximately equal to 24.4 degree. So once light enters a diamond, it is very likely to undergo total internal reflection inside it. Diamonds found in nature rarely exhibit the brilliance. It is actually the technical skill of a diamond cutter which makes the diamond or which makes diamonds to sparkle so brilliantly. By cutting the diamond suitably, multiple total internal reflections can be made to occur. Next again we are discussing about the technological application of total internal reflection, that's in the case of prism. Prisms are actually designed to bend light by 90 degree or 180 degree or to invert images without changing their size. Make use of total internal reflection actually. In the first figure you see we have an object AB here. The prism has bent the rays by 90 degree. You can see that this object is like this. Then when it has bent by 90 degree in the anti-clockwise direction, we will get the image of that object like this now. So here we get the image which is changed by 90 degree with respect to its initial position. So here these rays are actually not refracting to this side. Okay, this is the ray which is coming from the top part of the object. It is not getting refracted to this side. And this is a ray which is coming from the bottom part of the object, and this ray is also not getting refracted to this side. Okay, so here these light rays are not refracting to the other side. It is internally reflecting to this side. Okay, so here the critical angle, here the normal has drawn here. So the angle between this incident ray and the normal will be 45 degree here. So for internal reflection to be taken place here, this angle, the critical angle of this prism must be less than 45 degree. Then only total internal reflection would take place, because we know that for when the angle of incidence exceeds the critical angle, total internal reflection takes place. So here the angle of incidence is 45 degree and total internal reflection has taken place here. So the critical angle will be less than 45 degree. And here you can see that this ray is actually coming from air entering to prism. But we haven't drawn a refractor ray here actually. Why? Because you can see that this is the point of incidence now. So when we draw a normal, this ray is actually passing along the normal. So there won't be any deviation in its path. Similarly, when it is reflected back, when it is reflected internally to this side, again this is actually traveling in such a way that it is traveling along the normal to this point of incidence. Okay, so there won't be any change in their direction. That is why it is drawn like this. Alright, now you see this second figure. Here you see these light rays are one is from the top part of the object, another one is from the bottom part of the object. these rays are 2 times internally reflecting. You can see that it is getting reflected from this side, again from this side. So 2 times internally reflecting, and we get an image here which is went by 180 degree. Okay, 90 degree will be like this, again 90 degrees. So you will get an image like this. Alright, and here too the critical angle for the material of the prism must be less than 45 degree, because when we draw a normal here, we will get the angle as 45 degree, just like this. So for internal, we know that total internal reflection takes place when the angle of incidence exceeds the critical angle. So here the angle of incidences will be 45 degree for this side and for this side. So critical angle will be less than that 45 degree. Alright, now in the third figure, here also you can see that total internal reflection is taking place. Here you will get the inverted image of the object, but image will have the same size as that of the object. You can see that this is the ray which is coming from the top part of the object, and we are getting that ray here. Okay, so top part image will be here. Then this is the ray which is coming from the bottom part of the object, and we are getting that ray here. So this will give us the bottom part of the object. So the image will be an inverted one, but the image will have the same size as that of the object. So here also total internal reflection is taking place. Next one is a case of optical fibers. Optical fiber is a flexible, transparent fiber fabricated with high quality composite glass quartz fibers. Optical fibers are extensively used for transmitting audio and video signals through long distances. Each optical fiber consists of a core and a cladding. Then plastic coating would be there. Then core is optically denser than cladding. When a light ray enters the core, the light ray refracts and enters the core. And it is designed, this optical fiber is designed to it is designed to enter the core in such a way that, it is designed to, the light will enter the core in such a way that, or it is actually designed to enter the core in such a way that the angle of incidence, okay, this one is the angle of incidence, angle between incident ray and the normal, which is drawn at the point of incidence. Okay. So it is designed to enter the core in such a way that the angle of incidence is greater than the critical angle. So total internal reflection takes place. It gets reflects back. Again total internal reflection takes place. Again reflects back reflects back, total internal reflection takes place. Again reflects back, total internal reflection takes place. So in this way the transmission of light occurs. In this way the transmission of light occurs through the core and finally comes out at the other end. Since light undergoes total internal reflection at each stage, there is no appreciable loss in the intensity of light signal. The main requirement in fabricating optical fibers is that there should be very little absorption of light as it travels for long distances inside them. In silica glass fibers, it is possible to transmit more than 95% of the light over a fiber length of 1 kilometers. So in this video, we have discussed about very simple topics, total internal reflection in nature and its technological applications. I hope you understood this. Thank you.